So this is the take-up of the homework that I've assigned for tonight. I did show you the solution for the ammonia molecule, NH3, but we'll go through that again just so you have it here on video. So the strategy when you're building a molecule using Lewis is just to write one atom of each element first. So we're going to start with our hydrogen, and it's got one electron in its valence shell, and so we ask ourselves, well, what does it want? It wants to gain one electron. This is all about identifying, assessing, and satisfying the needs of our atoms and our elements and our ions, and that's how molecular bonding or covalent bonding and ionic bonding occurs in the first place. Okay, it's all about getting that filled valence shell. So nitrogen has 5 electrons in its valence shell. So hydrogen says I want 1, nitrogen says I want 3. So we need 3 hydrogens to satisfy that stable octet of nitrogen. So from there we can actually just draw the, you don't need to highlight, you can just do by pen, I call it a hug, so they share, they share, they share. So this is the formation, these are 4 atoms coming together then to make our final molecule. And when you draw the molecule, covalent bonds are represented as solid lines. That's an important thing because in grade 12 chemistry, or grade 12 chemistry and biology, we get into the forces between molecules where we use dotted lines. So that is one particle of ammonia. Now, if we were to do this as simple particles, we would draw our 3 hydrogen atoms and our 1 nitrogen atom, and then that thing's going to fuse. Now, you don't have to do this, but you can. It's not a bad idea, just to give you the idea of what's going on. So, NH3, nitrogen with 3 hydrogens covalently bonded to it. This is obviously not the scale, but you can see that it actually goes from being 4 atoms into 1 molecule of NH3. So that's our first molecule for homework. Hopefully you got that right. I'm sure you did because it's on the blog, and away we go. But do show the space fill model, okay, where you just do the simple particles if you'd like, if that helps you to understand this a little bit better. The Lewis dot is a little bit more precise in terms of showing the sharing of electrons. So let's take a look at the next one. So we've got carbon and oxygen. Well, this one should jump out at us, right? So carbon, we like, I did that one first. There we go, 4 electrons. Oxygen has 6 electrons in its outside shell. So it wants to gain 2. Carbon wants to gain 4. And carbon, you might say, well, why does it want to lose 4? Isn't that the same? Well, ideally, let me draw this one a little bit different. Ideally, the thing is that carbon is a non-metal, so non-metals want to gain. So if carbon wants to gain 4 and each oxygen wants to gain 2, then they actually are going to share. Now I'll just use a highlighter just for effect. Okay, so this pair will share, that pair will share, so that forms what we call a double bond. Really complicated, okay? Scientific word there, double bond. So that's when you have 2 covalent bonds between 2 atoms. So our final carbon dioxide molecule, which you should be familiar with that word because we breathe this stuff out, looks like this. And we draw the lone pairs around the oxygen as well. Sometimes in biological diagrams or chemical diagrams you don't see that. You'll just see the C with the double bond to the O. And if we look at our space fill or simple particle, there's your carbon atom. And an oxygen atom forms here or is here, partners up here. So we got our 3 atoms, and they are going to covalently bond to form a carbon dioxide molecule. With carbon in the middle. And 2 oxygens on either side of it, fused into 1 particle where they share, and their atomic shells actually will overlap, believe it or not. So it does become 1 particle in truth. Now there's another method that can be done where we actually show the covalent bonds between the particles, and that's literally called ball and stick, like Tinker Toys, okay? And we use these kinds of models in class when we build molecules, and we'll do that tomorrow. So we're going to draw our 2 bonds there with a carbon in the middle and a hydrogen, or sorry, not a hydrogen, an oxygen on that side and an oxygen on that side. So that's another way to represent the carbon dioxide molecule. All right? Whoops, using simple particles. Okay, so that's number 2, carbon and oxygen. So carbon dioxide. Solution number 3. Well, this should be fairly straightforward. Then we start with carbon. Again, 1, 2, 3, 4. Okay, so carbon wants to have 4 electrons. Each hydrogen wants to have 1 electron. So they cut a deal and it can single bond, just like this, in 4 locations, and form our thing called methane, the methane molecule. And that is what we were a little worried about last Thursday, a week ago, was leaking into our the atmosphere in our school. We had that gas leak, and away we went. But fortunately, the concentration of the methane was so low that we could have walked through with a blazing torch and nothing would have happened. It wouldn't have ignited at all. Okay, so let's just draw some space fill here. 1, 2, 3, 4, and that thing's going to turn into a methane molecule. Okay, so 1 particle, CH4. Okay, and again, if you wanted to draw a ball and stick, then you would just draw the bonds between the simple particles, and it would look like that. But I don't do that because that's forming, so I again want you to have that concept that it's 5 atoms coming together to form 1 molecule. Okay, so this particle formation, that's the whole idea of chemical change, is we start with some particles and we turn into others. Okay, and obviously if I'm drawing the atoms by themselves, I'm drawing the transition complex when old bonds from whatever the original starting substances were have been broken and new bonds then form. So we're kind of drawing from the during reaction through to the end of the reaction when we show this molecular formation using Lewis dot. All right, our final one. And this should be pretty straightforward by now for you. But there's lots of different complicated molecules. I mean, we are made of these things called biomacromolecules, really huge molecules, DNA, proteins, sugars, lipids. It's incredible. All right, so we've got a hydrogen. It wants to gain 1. We've got our friend carbon. It wants to gain 4. And we got nitrogen. And remember, as long as you're getting the electrons right, you can draw that lone pair in any of the 4 quadrants, which leaves those unbonded electrons oriented nicely for the triple bond that's about to form. Okay, so carbon says to nitrogen, well, I'll share 3 with you, and nitrogen goes, okay, that's cool, I'm good, I'm happy, I'm satisfied, I've got my stable octet or my filled valence shell, and hydrogen only needs to gain 2, so we don't really call it a stable octet, although that word is still used. Okay, so that's the covalent bond about to form, and we'll show that final molecule here. So H to C, triple bond to N with the lone pair on the end there. Now this is a dangerous substance called hydrogen cyanide. Not really a health food. It stops your electron transport chain, actually shuts down your mitochondria, and if you shut down your energy systems entirely, you're going to be kind of entirely shut down yourself. So if you've ever heard of hydrogen cyanide poisoning or cyanide poisoning, this is the chemical that is used, and no, you can't have any. So let me just draw my little forming atoms here and how they come together into our hydrogen cyanide molecule. Okay, so 3 atoms form into 1 molecule of hydrogen cyanide. And that's what that molecule would look like if we were doing space fill. So space fill, you don't show the bonds in between. Ball and stick, you actually do show the bonds in between. Okay, either or. All right, and if I require one or the other, I'll let you know. Okay, but for now, let's just use simple particles like that because they're really easy to follow and to count and track. So there's your solution to your homework, and I hope that helps. This is Mr.